and welcome. We are going to be wrapping up the course this week. So yes, we have made it. We have made it to the end of the course. Now it's time to review some things that we've learned and to put a bow around this experience that we have had thus far. Early on in the class, I started every class with a COVID update. It started with an example of looking at the graphing that we did with COVID testing, with the number of cases and deaths and so forth. But I thought, what better way to wrap this up than to review where we were and where we've come, because it's something that is at the center of what we are living with today. Now, these are the total cases reported here at our college. In order to give a little more perspective, I've added the data that I had saved from the first 4 or 5 weeks before the semester started, and I've put that in context. You may recall that at the beginning of the semester, the y-axis went to 150. By the second or third week of the semester, the y-axis had to be adjusted to 450. And so I have adjusted the original data to fit within the same scale as what we see for the remaining data. What we see is that early surge, topping 383 cases early in the semester, dropping down, and now starting to increase here toward the end. I've told you before that one of my favorite things to do is make predictions, and it turns out I'm not very good. I don't feel badly about that because actually most people are not good at making predictions, especially as they involve the future. And so let me tell you some of the predictions that I got wrong. I thought there was no way, when we began college in the fall, I said there's no way we're going to make it to October. The school will have to close down again. We're not going to make it to October, and I was wrong about that. And I'm actually kind of gratified to be wrong about that. I'm gratified to see the decrease in cases as we've gotten those cases under control. We've done a lot more testing, so I think that says something good about the direction that we are going. Another prediction that I made was that we were going to see exponential growth. Here I've fitted an exponential growth curve to the data. These are the data really running through the end of August. And what we saw was that those scores actually continued to drop off after that. So what we expected to see, the exponential growth, didn't come to pass, at least throughout the duration of the semester. So here is the current state. And the thing about showing you this is that no matter what I show you, by the time you see it, it's going to be hopelessly out of date. So this is really just to document where we are at this moment in history. We started at the end of February with no cases, no deaths. And from February until now, we are approaching about 250,000 American deaths. 1/4 of all of the COVID cases that have occurred in America have occurred since the election. In the last month, fully 1/4 of the cases that we've seen. That is an exponential increase. But that's the reality that we're living in, and the one that we'll be living in for a while longer. But my hope and trust is in science and the bringing forth of vaccines and such that are going to help move us through this. And wow, I can't wait for that time when I get to talk to you face to face without the mask, when we get back to some semblance of normal. So the thing that I really want to do with this session is to review the course. Let's go back over what have we learned. Now necessarily this is just going to be some highlights, but let's review what we've learned about in this class thus far. Early in the semester, we reviewed hypothesis testing. So we reviewed things like samples and populations. Our population, that's the entire group to which our theory is applied. That's the group about which we want to know something, but we can't test all of them, so we draw a subset, a sample from that population. We study the sample, take what we learn from the sample, and apply it back to the population. If our sample is representative, if it accurately reflects the characteristics of the population, we're going to learn a lot from that sample. We're going to learn a lot about the population. How might we get a good representative sample? Random sampling is the best way to get a representative sample. However, random sampling does not guarantee a representative sample. So the best way to improve our estimators, the estimators of our population parameters, is to increase the sample size. We're going to use our sample to make some inferences about our population. Again, taking what we learned from our sample and applying it to the population. When we do our tests, there are ways that we may determine whether or not there are statistically significant differences. And one is to establish a critical region. These are scores that are unlikely to be obtained if the null hypothesis is true. When is a test more likely to be statistically significant? So imagine that we're comparing two groups. Each has a mean and a standard deviation. Mean and standard deviation of group A and group B. The test is more likely to be significant if the variance between these two samples is small. If all of the scores in A are very similar to each other and all of the scores in B are very similar to each other, it's easy to tell which group they've come from. If the mean differences are large, so if the means are close together, it's going to be harder to distinguish the difference. But if the mean differences are large, if the difference between the means are large, it's going to be much easier to figure out which group scores belong to. And then also when the sample sizes are large. It's easier to spot differences, larger differences than smaller differences. So our test is most likely to be significant when the variances are small, the mean differences are large, and the sample sizes are large. How then do we measure statistical significance? Well, there are three ways to tell if the test is significant. So these are all telling us the same thing. This test is statistically significant. The opposite of these would say not significant. So we're going to focus just on a test is significant if, look at first of all the probability. If the probability of gaining these scores, of observing these scores, is less than 5 out of 100, less than p of 0.05, then the test is statistically significant. We can also look at the test value itself and compare it to our critical region, the cutoff score for our critical region. If the test value, the t or the f or the chi-square value, is in the critical region, the test is significant. And third, we can look at the confidence interval. Our null hypothesis hypothesizes no difference or a difference of 0. Therefore, if the confidence interval does not include 0, the test is significant. Another way of thinking about that is if let's say the lower confidence interval is in the negative range and the upper confidence interval is in the positive range, well, in between the negative and the positive is 0. So if one is negative and one is positive, it crosses 0, that would be non-significant. If they're both on the same side of positive or both on the same side of negative, it is statistically significant. So those are three ways that we can tell if our test is significant. What kinds of tests did we learn about? Well, we learned about the independent samples t-tests, comparing two groups, two independent groups. One of the assumptions for the independent samples t-test is homogeneity of variance. That means that the variances in group A are approximately equal to the variances in group B. To test this, we use Levene's test. Now, assumptions tests are different than means tests. We were just talking about a test is statistically significant. But when we're testing for group differences, we like and expect and would hypothesize and hope, that's why we're doing the research, we would like them to be, we would like the means to be different. They are different from each other. But our assumptions are meant to be met. So we want our data to not differ from the assumptions. We want them to be the same. In other words, we want these assumptions tests to be non-significant. So with the Levene's test, testing homogeneity of variances, if Levene's test is non-significant, we're happy about that. It means the variances are approximately equal. But if Levene's test is significant, that means the assumption of homogeneity of variances has been violated. The variances of the two groups are not equal. And so what do? The best alternative is to use a Welch's t-test instead of the independent samples t-test, what is sometimes called student's t-test. We also learned about paired and repeated t-tests. For any type of t-tests, we are always measuring only two groups. Never one, never three, it is two and only two groups in independent samples t-tests and paired samples t-tests. Well, next we learned about correlation. I taught you about Pearson's correlation coefficient, which is abbreviated as R. The Pearson's correlation coefficient tells us the strength and the direction of the relationship between two scale variables. It ranges from -1 to +1. We'll never exceed those values. Values closer to either -1 or +1 are stronger. Values closer to 0 are weaker. So the strength of the relationship is measured by how close the Pearson's correlation coefficient is to either positive or -1. And the direction of the relationship is defined by whether the Pearson's correlation coefficient is a positive value or a negative value. Negative coefficient means a negative relationship between the variables. Some things that we learned about correlation that are important to always keep in mind. Correlation shows us a relationship, but correlation does not imply causation. We're not saying that because two variables move together that one is causing the other one to move. There may be a third variable that's explaining both of them. Also, the R does not stand for relationship. The R in a Pearson correlation coefficient stands for regression. It's referring to that regression line that runs through the middle of our scatter plot. If we square the correlation coefficient in R squared, that gives us a measure of effect size. And this is called the coefficient of determination. The next type of test we learned about was the ANOVA. Whereas t-tests, we can measure two groups and only two groups. With ANOVA, analysis of variance, we can measure three or more groups. Now, technically, we could do an ANOVA with only two groups. The square root of the F value would be the t-score. But typically, we save ANOVA for three or more groups. What this solves for us is the problem of probability pyramiding. When we do multiple t-tests, each t-test has a 5% chance of being an error. If we do one t-test, we have a 5% chance. But if we do three t-tests, we have multiplied that error. 4 and 5 and 6 t-tests, multiple t-tests, we multiply the error. We solve that by using the ANOVA. The independent variable in an ANOVA is called a factor. So let's say we have three colleges that we are comparing. Well, the college is the factor. We have one factor, and that college factor has three levels, which are called groups or treatments. So the levels of the factor are the treatments. There are two sources of variance that we are measuring with our analysis of variance. Variance between and variance within. Variance between is caused by an effect plus some random error. Variance within a group is caused just by the error. We will divide variance between by variance within. It cancels out the error, leaving us with a measure for the effect. If there's no effect, if we're dividing error by error, then our f-test will be non-significant. And in that case, the f-value would stack up around 1. The further that our f-value is from 1, the more likely it is that our test will be statistically significant. And if it is significant, we will follow up a significant ANOVA with a post hoc test. This allows us to determine which of the 3 levels of our factor is different from which other levels. So from there, we moved into studying about simple linear regression. All forms of regression are about the same thing, that is about making predictions. With simple linear regression, we use one variable, the x variable, to predict a y variable, which is our outcome. X is the predictor, y is the outcome. Now with a simple linear regression with just x and y, that's really the same thing as a correlation. And in fact, anytime we do a regression, we need to check the correlations between the variables that we're using. We want to use correlated predictors. If 2 variables are uncorrelated, there's a good chance that that predictor isn't going to tell us anything about the outcome. So we do want to use correlated predictors as part of our model. Multiple linear regression, instead of using just one x to predict y, we'll use multiple x predictors to predict that singular y outcome. Multiple independent variables to predict one dependent variable. We can add those predictors one at a time, and then we can test the model at each stage to see whether adding an additional variable as a predictor improved our model. When we do that, we use an f-test, an ANOVA test, to determine whether the addition of the extra variable contributed to the predictive ability of our model. If the predictor is non-significant, we are not going to include it or leave it in the model. If the predictor is significant, if it's contributing to the model, it's something that we typically would leave in. As we studied regression, we learned that there were assumptions built into the regression equation, to the test that we were using, and it was very important that we always make sure that our variables meet those assumptions. Among the assumptions we learned about were linearity, that the scale variables are linearly related. That we can test using a scatter plot. Put a regression line through the scatter plot, see if there is a linear relationship. Homoscedasticity. That means that the variability of the dots around our regression line is pretty much the same at every level along that line. They're not cone-shaped or round. They are consistently spread out along our regression line. And one way to see this is also with the scatter plot. Now, autocorrelation, sometimes called first-order autocorrelation, and multicollinearity are similar ideas. We don't want the predictors in our model to be too strongly related, essentially measuring the same thing. We would like them to be strongly related, especially to the dependent variable, but not too strongly related to each other. We test for autocorrelation using the Durbin-Watson statistic, which is a test that runs from 0 to 4. We are looking for a Durbin-Watson statistic around 2. That is most desirable. If you get above 3 or less than 1, we're starting to see some autocorrelation. That is something that would need to be addressed in our model building. Outliers. An outlier is a score that is very far from the other scores. It lies further out. But we would define this as a score whose residual error is much larger than the rest of the residual values. In fact, that is how we will identify an outlier. We're going to look at the residual statistics to find out if there are values that lie typically beyond the 3.29, above or below the mean. Outliers can affect the strength of a correlation. They can make it look stronger or weaker than it truly is. Outliers can also affect the direction of a correlation. They can change the slope of that regression line. So it's very important that we address those outliers before we do our modeling in our regression equation. The chi-square statistic is a non-parametric test that we can use when we do not have scale level data, but we have nominal level data, perhaps some frequencies or some count data. Now, because it is squared, chi-squared, you can count on the chi-square to always be a positive number. Right? Anytime you square a value, it makes that value positive. Squaring a positive stays positive. Squaring a negative becomes positive. The degrees of freedom for a chi-square, unlike most of the tests where we use n-1, for the chi-square it is k-1, where k equals the number of groups that we are measuring. And when you do a chi-square, it's very important that you check the observed frequencies and the observed and expected frequencies, and make sure that you have a minimum of 5 in each cell. Now, chi-square is just one type of non-parametric test. There are many others, and each non-parametric test is an alternative to a test that we have learned about. So, for instance, the one-sample t-test is the parametric test, and its non-parametric alternative is the sign test. Instead of the independent samples t-test, the non-parametric alternative would be the Mann-Whitney test. Paired samples t-tests will be the Wilcoxon signed ranks test. The one-way ANOVA is a Kruskal-Wallis test, is our non-parametric alternative. And Pearson correlation, non-parametric, we could do a Spearman rank correlation. Many of these follow the binomial distribution. And then we learned about time series analysis. So there's all kinds of variants that we learned about with time series analysis. There's the horizontal time series. It's where the data fluctuate around a constant mean. They go up, they go down, but they stay on the average about the same. Seasonal time series is repeating variability. It goes up, it goes down, and there's a consistency in the time, the season in which it occurs. But it does not have to be the 4 seasons, spring and fall and summer. It could be as short as a single day. Maybe there's an increase in calls to the call center first thing in the morning, and it drops off, and then increases again around noon, and then drops off again. So we see a seasonal time series occurring even within the course of a single day. Now, cyclical time series, that's an alternating sequence that goes above and below the trend line. But what defines this is a cyclical time series lasts more than 1 year, making it different than the seasonal time series. A trend time series, these are more gradual movements to higher or lower levels. Like we're seeing over time, we're seeing a gradual increase in sales. Now there's always ups and downs, but over time we're just seeing a gradual increase. It goes up. That's a trend. This is easy to spot with a simple linear regression. And then vertical time series plots have their use, but one of the uses is not to identify data patterns. It does not tell us very much about them. Because of the up and down in our time series, it's nice to smooth out that variability, and we use that with smoothing constants. It smooths the pattern of the up and down, gives us a cleaner picture of what's actually happening over time. And we use different exponential smoothing constants. If we use a constant of 1, that would be equivalent to a naive forecast, one where we are actually not making any assumptions about the smoothing the value. Moving averages is another forecasting method. It's used when the time series has no significant trend, there's no cyclical, there's no seasonal effect. We just use moving averages to just help smooth out the overall forecasting method. Some variables, however, show a curvilinear trend. Instead of being represented by a straight line, we see a curvature to that line. This can be modeled using an expansion on the general linear model. And what you're doing when you're estimating a curve in your general linear model is you're introducing an exponent. We might take a time as being one of the predictors, but we would also introduce time squared, and that exponent is going to create a curvature within the line that we're using for prediction. Well, that is a quick review of the things that we've learned about in applied business statistics this semester. So that's pretty well wrapping things up. I do want to thank you for being part of the class. Thank you for watching the videos. I wish you the very best as we move on through life. Those of you who are students, please feel free if you want to reach out to me through email. If you have questions, whether it's about the final, about tests, or as you continue your education, I always love to hear from people. One of the things I've missed the most about the changes that we've had to make is that I haven't been able to meet people face to face. So I still want to be able to be there for you and make that connection. So do feel free to reach out. Well, that's everything we're going to cover for this week. So again, thank you very much, and I wish you the very best with your life and with your education. Oh, you know, there's one more thing. One more thing that I have wanted to do all semester, and this is the last video, so what better time? There's one more thing that I wanted to do this semester that I have not had the chance to do. It's going to be a while before we get to do that in our classrooms again. But we're going to get through this. Someday, we will be able to see each other face to face again. I miss that more than anything as an instructor, and I think you probably do too as a student. We're going to get through this. We're going to care for each other. We're going to be safe. Thanks for being part of the class.